Hey everybody, one of the things we've done so far in this class that is so fundamental is the idea of taking a function and then finding its tangent line. And I've mentioned to you before that we like to use tangent lines to approximate the values of a function. And in this video, I'm going to give you more detail on that, talk about a little bit of the theory behind that, and introduce a few more formulas. So let's go back to the beginning, to what we know. So if you have a function, we like to say y equals f of x. I'm going to reserve y for the tangent line, and here just talk about, say, function f of x, and say that you've picked a point x equals a, and then the y value would be f of a. And so what's the tangent line to the function at the point a, f of a, if it exists? So we know by now that that formula is given by the slope is f prime of a times x minus a, and then minus, or plus, f of a. So that's the formula for the line tangent to f of x at the point x equals to a. And there's a fancy name for this. It's called the linearization of f at the point a. We use that name just because this is the graph of a line. We've taken f of x, it's nonlinear, we've linearized it, and we use the point a, f of a. And so you'll see people write L of x equals that formula. And you'll hear it called the linearization, and you'll also see it just referred to as y. So y and L of x are interchangeable throughout this video. And so say that you've done that. Say that you've got some function. I'll draw you a picture of some function. And say that you've picked a point a, and there's your point a, f of a. And now for any other point x, I'm just going to introduce some more notation. So we talk about this idea of a small change in x and what happens. So I'm going to call delta x. We use the Greek letter capital delta to represent a small change. That's always going to be x minus a. So you fixed a point a, and then for any x, you can talk about delta x. You can talk about delta f equals the actual change in the function. And I want to try to illustrate that here on the picture a little bit. There's a couple things going on. So let me draw the tangent line, L of x. That's what that looks like. And here's a, f of a, and if I walk up from the point x and find f of x, then that's right there. And if I go over and I go up, well, where's delta x on the picture? So here's delta x. It's x minus a. It's that distance from x to a. And where's delta f? It's the change in the y values. So you're looking at the change from, so here's f of a and here's f of x. So this entire dotted line here, that's given to me by delta f. Sort of write it over there. And another thing that I'm going to look at, we talk about this quantity in calculus. We say dy. So I could just say delta y representing a change in the values of the tangent line. It's interchangeable. So this is like y or function L at the point x minus function L at the point a. And it's just this portion from well, L of a and f of a are the same value, right? So they both start here. But then delta y, the change in the tangent line, only extends up to the yellow part. So that's delta y. That's another name for dy. The reason why people use this dy notation is because later on in higher mathematics, you'll generalize this to something else but keep that same notation. The way you should think about it here is that when you're talking about a function, you're going to want to talk about delta f and delta x. When you're talking about tangent line, think about dy and dx. And these just mean delta y and delta x. And when I first took calculus, I thought it was kind of confusing to have delta x, delta f, and dx, dy. They kind of, like, why not just use delta x, delta y? But the reason is to sort of distinguish between the level of a rate of change or a change in the values of the tangent line versus the change in the values of a function. So I want to ask myself, how are these things related? And if you go back to the definition of the derivative, remember that definition of the derivative, it says, well, you take a limit, and you're taking a limit of a difference quotient. It's f of x minus f of a, that's delta f, over x minus a, that's delta x. And you're taking the limit as x goes to a, or in other words, as x minus a goes to 0. So you can think of this as a limit. It's delta x. Goes to 0. That's another way of writing the derivative at the point f of a. So two things about that. What we're going to say is that if delta x is small enough, if it's close enough to 0, then you'll see the tangent line will be pretty close to the actual function. So you'll be able to write an approximate equation. You're going to be able to write, I'll put it up here, that delta f over delta x is approximately, use that wavy line to say approximately equal to f prime of a, at least when delta x is small. And if I just bring delta x to the other side, you get one of these fundamental linear approximation equations which says that the change in values of f is approximately equal to the derivative at the point f of a times the change in x. And that's just the mathematical way of saying that this distance is pretty close to that distance so long as x is close to a. No big deal. And there's one more formula that I want to show you. If you go back to that tangent line formula over there, if you bring f of a to the other side, so you get L of x minus f of a. And remember how we saw that f of a is equal to L of a. So if you bring that f of a to the other side, what you'll end up with is L of x minus f of a, which is equal to L of a. And that's equal to f prime of a times x minus a. So that's equal to f prime of a times delta x. But what's this equal to? That's nothing but our notation for dy, the change in the y values of the tangent line. So you can get now this formula, dy is equal to f prime of a times delta x. And you can use delta x or you can use dx whenever you want. But usually when you're using dy, you use dx to go along with it. So at the level of the change in the y values of the function, they're approximately the derivative times change in x. At the level of the tangent line, the change in y is exactly equal to the slope times the change in x. So those are your two fundamental formulas for linear approximation. We'll put them to work in a separate video and do some examples. I just want to show you one more thing before we go. We're often interested in measuring how good of an approximation that's equal to. So in other words, we're interested in the difference or the absolute value of the difference between this delta y and this delta f. So if I look at this difference here, we're going to call it the error, E for error. And so what's the formula for that? Where can I write it? I'll put it down here. I'll say that what we call the error, it's going to be the distance. So I'm going to use absolute value to make distance. That's going to be the change in the function from x to a. I need to subtract from it dy. And I know that dy is just equal to f prime of a. And since I'm using deltas, I'll keep it as a delta x. It means the same thing, x minus a. So this is called the error. It represents how good this approximation is. So it tells you how close you are to actually approximating the value of the function. Later on in the course, once we learn the mean value theorem, I can show you a way to ensure that this error is always going to be small. Or in other words, I can show you how small to choose delta x in order to make the error as small as you want. You can do that so long as you know that the second derivative of the function is, well, first of all, exists, and second of all, is bounded near the point a. It's actually the second derivative that controls how fast that function curves, how fast it can curve away from the tangent line. So that's the theory behind linear approximation. We'll put it to work in a separate video.